And thank you for inviting me here. I didn't know about the background of the audience, so I tried to explain all the concepts from the basic and try to explain the major points of the crucial issues in designing systems, embedded systems on multi-core platforms. There are many issues, of course, so I try to focus on some of them. We all know that the evolution of embedded system in several domains, from small devices up to very big systems like aircrafts and cars, and each application has its own specific issues to be solved. One of the most typical domains is a car. The number of processors in a car grew exponentially. And today there are more than 100 processors in a car, in the most advanced of cars. And same thing in the small device like a cell phone. Same exponential growth, and the number of functions also increased exponentially. And this trend is going to increase in the future. So by looking at these trends, we can see that there are several things that characterize the software for embedded systems. First of all, there are an increasing functionality, need for more and more functions. And this is, of course, driven by user requirements. This means increasing software complexity. From another hand, also the hardware platform is evolving even more quickly than software. So every month, basically, there is a new platform that is delivered. So people is interested in using this platform for satisfy performance constraints. And the third requirement is exactly performance constraints. People want a high performance and real-time requirements in order to make systems more and more effective. So trying to combine this requirement is not easy. So let's see in terms of design objectives. So from one hand, we said there are increasing functions we know to incorporate in embedded systems. But we have also high performance requirements, and at the same time, very often we have multiple applications running on the same platform. And of course, we need to deal with fast software and hardware evolution. So from these two requirements, we need basically high processing power. And this means that's why we try to use multi-core platform, because single processor cannot be more powerful than they are now because of energy efficiency reasons and the power consumption. So the slowly hardware designer moved to multi-core platforms. And from this means also that we need to exploit this parallelism. So there is a need for specifying the parallel structure of our programs in order to fit into this parallel hardware. And from these other constraint requirements, high-performance requirements, in some applications, especially in control application interacting with the environment, there is a need of satisfying some real-time requirements, meaning periods for control activities, periodic activities, or deadlines for other general activities. Whenever we have to run multiple applications in the same system, we want to follow a component-based approach, because typically different applications are developed by different teams, different groups, and sometimes they don't talk to each other. So the idea would be to develop and also verify the application in isolation, like having an individual component to run each application. But then we need to put different applications together in the same platform. So this is essential to make things working when they are developed. They are coming from different teams and verified independently. And then, since the hardware is changing so fast, we need high software portability in order to move the same application from one platform to a new one. And also, a real-time guarantee together with component base demands for temporal isolation, which means basically trying to verify the performance requirements in isolation, application by application, trying to avoid reciprocal interference. So basically, my talk will be about these issues, how to achieve these properties. So let's try to identify one issue at a time. So from one end, we would like to optimize resource allocation, because most embedded systems have not many resources in terms of processing power, memory, and so on. So we would like to optimize resource allocation, but at the same time manage the parallelism. On the other hand, we would like also to simplify portability, because we said there is a high probability for moving the application in different platforms, and try to isolate the timing behavior whenever we change platform, or we want the system to continue to work even on the faster platform. And but this is not so trivial. So we would like to isolate the behavior of different applications, and at the same time providing some offline guarantee for critical application, for aircraft application, for example, but also for automotive application. We need some offline guarantee, especially for critical activities. So in particular, this talk will focus on these three issues. One is to illustrate a general framework to address such multiple objectives. Then I try to present a number of consolidated methodologies for handling specific problems. And then I will conclude by stating a number of open problems for future research investigation. So I believe that the most important part is to build an appropriate model. Whenever you want to approach a complex problem, it's essential to start with a proper model. And in this case, the model is to consider a number of applications that can be independent. Think of cell phone apps, for example. They are pretty much independent, developed also. And you need to execute these applications on a multi-core platform. So finally, you need, each application is parallel, so it's characterized by a number of tasks, a number of activities that may interact with each other. Finally, you want to execute these individual activities into different cores and try to satisfy timing constraints, some performance constraints. Now, how to achieve this goal? Well, this is the problem we need to solve. So how to map these individual tasks into the hardware. So we have to solve not one, but different problems. So let's identify problem by problem which one we are going to address. So first of all, how to express parallelism from the application level. Second is how to achieve temporal isolation, how to partition each application in isolation. Then how to analyze real-time properties and try to guarantee some real-time behavior in advance. Then another issue is portability, as I said. And of course, we would like to optimize, to use the least possible amount of resources in order to limit the cost of our system, or given a platform, try to execute as much as application we can. Well, each of these problems, it's a big issue. So I don't have time, of course, to deal with all of them in details. But to exploit parallelism, one thing we are sure that sequential programs, like written in a sequential language, are not no longer the most appropriate way to specify, a program. So most of the time, the user knows exactly the specific features of the program, so it's the only one which can say which part of the program can be parallelized. And so we need a language in order to specify that and try to exploit this information in order to optimize the allocation. Now, it's intuitive to understand that the more we parallelize, the better we can achieve. But it's important to understand that the parallelism should be achieved for the entire application, because if we have a sequential program and just we are able to parallelize only a fraction of that, let's call gamma this fraction. This means that when we move to a parallel architecture using P processor, we of course parallelize this fraction into P processor, let's assume evenly for now. So it's important to measure the gain we made, and this gain is typically measured by what we call speed up factor, which is basically the ratio between the completion time that we can achieve on a uniprocessor platform divided the completion time on a P processor. So it's a function of P. And by this picture, you can see basically that this speed up factor is equal to 1, because this we consider a unitary program, 1 divided by this factor. And if we plot this curve as a function of gamma, as a function of fraction that we parallelize, we can see that in order to really achieve a benefit, we need to parallelize a lot. In fact, if we have 100 processors, suppose we are able to parallelize only 50% of our code, we just achieve a speed up factor of 2, which is not the best we can do, because we have hundreds of processors. So you can understand from this picture that it's really important to exploit parallelism in this region. So we should be able to parallelize 90%. This is the things that really we can exploit a parallel platform. So how to express parallelism? Well, there are many ways. One is using a data flow language. I discovered today that also people here in this university is working with the CAL language, developed the University of Berkeley in 2003. This is a possibility. This is based on actor concept, which is a set of actions that can be run in parallel depending on input token that are derived from other actors. So basically each action reads an input token and modifies the internal state of the actor, and then produce some output token. They go into buffers. So, and then you can build your application, which is intrinsically parallel in this case. This is one way. Another way could be using annotation, using a sequential code by using annotation into the code in order to specify parallelism. This is also a used approach in different environments. But at the end, once you specify your application parallelism, you should be able to draw kind of graph, which is actually a DAG, directed acyclic graph, which specify the highest possible parallelism. So in this representation, basically, you have the highest possible specification in terms of parallelism. So this means that each node of this graph represents a sequential portion of code that cannot be parallelized anymore. So you have, in this way, you express the largest possible parallelism. Of course, you can merge. If you don't have enough processor, you can merge nodes into the same processor. But in this way, you have the largest degrees of freedom that you can exploit. So once you have this graph which specify the parallelism, the next thing you have to do is to perform some analysis. So it's important to define a right model also for this application. So in other words, there are several things you need to decide. First of all, the arrival pattern. So how this application is generated, by event or by time, by periodic activation. So there are several possibilities. This depends on the specific case, on the specific case study. So periodic means activation exactly separated by a period which is given, or which must be determined by performance requirements. Or the application may be generated by event. This can be sporadic if there is a minimal separation between events, or can be generally aperiodic if there is no bound between inter-arrival times. Then another thing you should decide is whether the application is preemptive or not. So once you start executing a task, can you interrupt the task because another important application arrived or not? This is also another important decision to be made in order to perform the analysis. And of course, you may decide for a fully preemptive application or fully non-preemptive application, or something in between, partially preemptive application. So maybe the application can be interrupted only at specific points, called preemption points, for example. Also, another important point for the analysis is migration allowed between processors. So basically, you perform a static allocation, or you allow tasks to move from one processor to another. This makes a big change in terms of analysis. And then you have to provide also a number of parameters in order to make the analysis. And the most typical parameters are the computation times for each activity here. So you understand that in order to provide the computation times, you need to assume a specific architecture, because computation time really depends on the architecture. By computation times here, I mean worst case computation time. So in the worst case situation. So in order to guarantee some timing behavior, I need to know computation time for each task of the application. I need to know a deadline for the entire application, and also if the application is periodic, I need to know the activation period. If I know this parameter, I can perform some analysis and try to guarantee timing constraints. Other important factors for the analysis are, once specified these parameters, are the sequential computation time, which is basically the sum of all worst case computation times, and also the parallel computation time. By that I mean the length of the critical path, basically the longest path in the graph. Why this is important? Well, because if the longest path is less than the deadline, then of course I may succeed to guarantee the behavior. Otherwise, for sure, there not exist any solution. Because by parallel computation time, I mean if I have infinite parallelism, okay, infinite number of processors, or if I have as many processors as I want. So if CP is greater than the deadline, then I can say that the application is not feasible in any number of cores, of course. And if I have the sequential computation time is less than the deadline, then A is feasible even on a single core, right? If the sequential program is less than the deadline, I don't need basically a parallel platform. So these are trivial case. This is a negative solution, let's say. This is a very positive solution. But the most interesting part is in between, right? When we have to work when these two conditions are not satisfied. So this is an example just to understand what the critical path is, right? Okay, so another important parameter is the utilization, which is the sequential time divided by the period. So this specifies the required bandwidth of our application. So how much fraction of computational resource we need. And we can derive some bounds in terms of number of required cores. For if we take the ceiling of this number and the ceiling of the twice of this number, this gives us for sure the number of cores is in between these two bounds. Okay, so now once we specify parallelism and we specify the parameters of our applications, the next question is how to achieve temporal isolation. So let me explain this concept because maybe not all of you is familiar with this concept. So temporal isolation is a property of a multi-application system, so like the model we considered at the beginning, in which the performance of a single application does not depend on the execution of the others. Okay? It depends only on the performance of an application only depends on two things. On the computational demand, basically on the size of the activities, and depends on the amount of allocated resources. Of course, right? If I allocate a very powerful processor, it takes less. But does not depend on the other applications. So this means that the interference is bounded. This is an essential concept in order to guarantee, simplify the analysis of very complex systems. So how can this be achieved? How can we achieve this property? One way is to have resource reservation. This is another concept common in a real-time environment that I would like to explain clearly because it's really important for future complex systems. Okay, so an isolated application, basically, we say about temporal isolation when an isolated application executes as it were executing alone on a slower dedicated processor. So you can forget basically all the other application. You just, he behaves like he were alone on a smaller processor, on a slower processor, with speed equal to the reserve fraction. So this means here that we partition our computational power into different fractions. And there are different advantages. First of all is predictability. As I said, a misbehavior of an application does not affect the others. This is really important. And it allows a modular analysis. Once I know the fraction of computational power I allocate to the application, I don't need to know information about other applications. So I can guarantee real-time constraints independent on the knowledge of other code. So each team can develop and also analyze the specific application. So this concept of resource reservation is basically a relatively new approach which is, can be compared with prioritized access of resource, which is a traditional way of looking at competing applications on the same processor. So in a traditional approach, you have different activities, different tasks, with different priorities that compete on the same processor. Of course, the highest priority task will win the competition and will be executed first. And then the other will be enqueued in the same queue. So they are executing in this order. But in the resource reservation approach, we don't think of competing with the same, on the same processor, but we partition the processor into different fractions. So for example, I allocate 50% of the processor to this task, 30% of the processor to this task, and 20% of this task. Once I partition in this way, then of course this activity runs in this subfraction like without experiencing interference from the other tasks. So you can think that if you think of an application of, as a flow which produces a variable load into your processor, clearly the highest priority task, in this case tau 1, whenever it has a higher demand, will steal resources to the other task. So the other task will suffer, so will execute less than needed, right? So you have a very variable execution in this environment. But while in this environment, you can think there is more isolation. So whenever there is a load increase, this load increase does not affect the other application, but only affects the specific task. So basically, it will slow down just in case of an overload, not the other ones. And this is essential for modularity and for also for the analysis, for analyzing individual applications. So just to make a comparison, you can think of priorities versus reservation as tasks as vehicles. So suppose you have different tasks, there's different vehicles with different priority. Right? Ambulance, of course, is a high priority. Police has a high priority. And then there's a medium priority and trucks low priority. And we have a shared medium, which is the road. So in a priority-based approach, we put everything in the same resource. So basically, they compete. But you see sometimes a high priority vehicle cannot run because of lower priority vehicles in front of him, which prevent it to run. So this is the interference I mentioned in task scheduling. Of course, this is really a big problem. So in the resource reservation approach, instead, we partition our resource into different fractions, and we allocate each type of task into its own resource. So in this case, of course, each activity has its dedicated fraction. There is much less interference. What's the disadvantage of this approach? The disadvantage is that if we perform a wrong allocation in an overload condition, this amount of computation will experience long delay, even though the other resources are not used. Of course, this will never happen to Italy, but maybe in other countries it will happen. So in Italy there is more dynamic resource allocation in the roads, but this is just to explain the problem. Well, in this case we need some additional mechanism which allows us to change the resource allocation on the fly whenever there is a situation like this, or the possibility at least to change. So going back to the resource reservation model, we need to partition our resource into different fractions that becomes a kind of virtual processors. So each fraction becomes a virtual processor. And each fraction is dedicated to a particular application. So once we partition the processor, we need to have a resource enforcement mechanism. This mechanism should prevent a task that requires, for example, more than 25% running in this fraction to steal resources from the other fractions. Otherwise, we lose the isolation, right? So we need a mechanism inside the operating system. This is an operating system mechanism. We should delay tasks that are trying to execute more than we allocate. So this is the mechanism that needs to be implemented in operating systems. And this is typically done by reservation servers. I don't have time to explain reservation server, but I give you an idea. there are several mechanisms that can be used to implement this enforcement mechanism. But once we have that, we can say I allocate a fraction of 25% to the server and I execute one task. But in this case, I can execute an application with 2 tasks and so on. And then, of course, I need to schedule all the servers together. And so I have a scheduling mechanism which takes all the reservation servers and schedule in a single CPU. For now, I'm considering just a single processor environment. So an example of server, a server is a way of providing service, right? In this case, of providing execution time, processing time. So for example, typically a server is characterized by 2 parameters. So I provide a computation time Q every period P. So my fraction is, for example, if Q is equal to 4 and P is equal to 10, my fraction is 0.4. So I provide a reservation equal to 0.4 to this application. Every time this server runs, the server allows the task of the application to use the processor. But in this slot, in this interval, the application is not allowed to run, but other applications are allowed to run. Of course, this is another example. If I have a more reactive application, then I may decide to reserve the same fraction, but with a shorter period. So I reserve 2 every 5 instead of 4 every 10. The fraction is the same, but you see the service is more frequent, and this is better for reactive application with less deadlines. So which one is better depends really on the application. But you can see that these 2 parameters are used to tune your allocation. So this is a specific mechanism, but that can be abstracted by considering 2 equivalent parameters, let's say. One is the fraction we allocate. So instead of thinking of amount of time Q every period P, we can think of bandwidth, the fraction we allocate, in this case 0.4. But you see, depending on the choose of this parameter, we may have longer delays. For example, in this case, once an application runs here, you may have to wait for a long time before the next execution. So we can compute the maximum delay delta between 2 consecutive executions. In this case, of course, the delay is less and still given by these 2 parameters. So in other words, it's easier to think about alpha and delta, bandwidth allocated and maximum delay. So we can see our system as virtual processors, where each virtual processor is characterized by these 2 parameters. So fraction of allocated bandwidth and maximum delay. And of course, by tuning these parameters, we can change the allocation, and then of course the quality of service of the corresponding application will be changed. So this is a more flexible way to control the performance of an application. And this is used, is the key point to implement hierarchical systems. A hierarchical system is a system built on a processor or a processing platform, which can be also multi-core. But the idea is that since this platform is very powerful, you can build subsystems, independent subsystems, and by using the reservation mechanism, and try to run each application independently. And you have these alpha delta parameters in order to tune and to allocate the fraction of this the total processing power available to each subsystem. So this is a key point, as I said, for the future, when because the complexity is increasing every month. So we need a way, this is a way to bound the complexity of the entire system by designing each subsystem independently and also analyzing it. Okay, now we reach the third point, how to analyze if these applications are critical. How can we analyze timing constraints? Okay, there are very well established techniques in this field. And the most general approach is the following. Suppose that an application is characterized by two tasks, and in this example, tasks are periodic. Okay, so the blue arrows identify the activation time. You see, are regular, so they are periodic, and the red arrows pointing down represent the deadlines. Okay, so these tasks cannot exceed the deadline, otherwise the system behaves very badly. So we don't want. So we have only this window for this task to execute, and the same for the other tasks, for the same jobs of the same tasks. So one way to analyze the demand, the computational demand of this application, is to define a demand-bound function. It's called. This approach was proposed in 1990 by Barua and other researchers. Basically, it consists of specifying the demand based on the deadlines and on the worst-case computation time according to this formula. Basically, for each task, so the summation is done for each task, we consider a step function which is equal to the worst-case computation time in the interval. So every time we cross a deadline, we increase by the worst-case computation time. So each task generates a regular step function, and then we sum all of them. Of course, they have different computation times and different periods, and also different deadlines. So this represents basically the amount of computation requested by the application in any interval 0t. In any interval, we know how much we need to execute. Okay, so now we have to characterize, if we have just one processor, an entire processor available for that application, in any interval t, we have available, what's the available time in an interval t? Of course, t, right? If we have a single processor entirely dedicated to that application. So in order to satisfy the timing constraints, we need to verify that the computational demand in any interval 0t is less than the available time, which is t. So basically, this means that this step function must be entirely below this line, which is the available time. When we move from a single processor to a reservation-based mechanism, of course, what has changed is that we don't have the entire processor available. We have just a fraction. So we can characterize this fraction in this way. This is the server execution. Whenever a server executes, we have a slope of t, the available time, but the server, when the server does not execute, we have, we keep the available time as before. We don't increase. So we have a kind of function like this. So now we need to verify whether our computational demand is below this function, which which represents the reservation, depending on the parameters p, q, or alpha, delta we dedicated to the function. So some people, well, this is the exact analysis. Some people, since the exact analysis may be too complicated, some people prefer to simplify this strange function with a much simpler function, which is a linear function characterized by an additional parameter delta, which is the maximum delay I told you before. and this will be the bandwidth alpha we allocate. So basically, this is not exact because we lose something, but it's much simpler to verify in terms of complexity. So in other words, to verify the feasibility of real-time application, we just need to verify whether the application demand in any interval is less than the new function, which is specific for a reservation. So now, let's see how we can simplify portability. Okay, if we follow a reservation-based approach, we already simplify portability, but there is still another step to do. To simplify portability, we should abstract the physical platform in one way, right? Because the design process is quite complex to take into account timing constraints. So we would like to perform the allocation not on the real platform, but so we have to abstract the real platform with a virtual platform. So a virtual platform here is represented by reservations. So the question is, how much bandwidth do I need for running application A given some timing constraints? Well, I can perform the real-time analysis and derive these numbers. So I need, for example, 20% of the processor for this application. For this one, I need maybe 50% of the processor. And then basically, I try to allocate each application into a virtual platform, into a reservation. And then in the next step, I try to allocate virtual reservation into physical cores. You see that if we change platform, we don't need to change the first step, which is the most complex one. Because allocation is a very complex activity, sometimes cannot be done in linear time or polynomial time. We need to, use optimization methods which are very expensive sometimes. Another question is, if we have a multi-core platform, how can we extend the reservation concept to take into account multi-core platforms? Does it make sense, for example, to define a reservation with alpha greater than 1? Well, let's consider this application. Very simple. We have 5 tasks, and this is a kind of precedence graph, right? So we can execute the first one, then we can go parallel, those 3 tasks, and then we join with another task. And the numbers inside represent worst-case computation times. Now, the question is, suppose we have a deadline equal to period equal to 10 units. Units are the same as expressed by computation times. You see that the sequential computation times is equal to 19 for this application. And so basically the amount of bandwidth required by this application, if t is equal to 10, is 1.9. Okay, so you may guess 1.9, we need 2 processors, right, to execute this application. Well, but unfortunately, we cannot execute the application in 2 processors. In fact, once you allocate these 2 tasks, you use the 60% of the bandwidth. You cannot allocate the 3rd task in either one of these processors. So even if the required bandwidth is less than 2, you need 3 processors in order to execute this application. So this simple example shows you that the total amount of bandwidth required by the application is not a very significant parameter. So you should know exactly how the computation is distributed in the graph in order to perform the exact allocation, a feasible allocation. So this comes from to the conclusions that a multi-core reservation must be specified as a set of uniprocessor reservations, not as a total, because the total doesn't make sense. So you need to specify a set of uniprocessor reservation, each one less than 1. So in this view, let's consider, for example, a cell phone application where we have a calculator, we have a camera, we have some player, music player. So we have 3 applications. We have a platform, a physical platform with 4 cores. And here we have a virtual platform, theoretically with infinite cores, because we can generate as many as we want, as we need. And then we perform the... So the idea is to specify first that each application is a set of graphs with timing, constraints, and parameters. Then we have to compute the exact processor demand for each application in order to see how much bandwidth we need. And so once we compute that, we realize that, for example, we need 2 virtual platforms for this, 3 for this, and 3 for this. And then finally, in the final step, of course, we perform the final merging with the physical platform. And we may realize that these 2 can be merged into 1 core. And also these 2 can be merged into 1 core for this specific platform. Of course, if in the future we change platform, then these 2 are more powerful. We can merge 3 virtual platforms into 1 core because this is more powerful. So you see, we don't need to change this allocation process, which is the most expensive one. Or even if we have an even more powerful, we can merge everything into 1. Or if we have a small, we can turn some core off to save energy, for example. And we can decide to play, you see that depending on the assumption you make, you have lots of variables to play with. If you have energy, of course, this is another dimension to consider. You may also consider temperature. If you have temperature, you may want to switch, if you execute an application here, the core heats up, so you may reach a critical temperature, so then you can switch off this by transferring the application to another core. So you have another dimension to consider. Okay, now let's move to the optimization problem of how to allocate a parallel application into a virtual platform. Of course, there are several possibilities. Suppose that we have this graph, a very simple graph. We can allocate this task into a virtual platform and this task into another virtual platform. And this is a possibility. But I can choose also another possibility here, and depending on the way I allocate, of course I consume more or less resources in total. So if I want to optimize the amount of bandwidth which I consume in total, this becomes a very complex problem. So for example, first of all, if I have a real-time constraints, I need to, in order to perform this allocation, I need to consider timing constraints. And one way to do it is to assign intermediate deadlines, because usually the deadline is assigned to the entire application. But then if I need to split tasks into different virtual platforms, then I need to assign virtual deadlines also to each task. And this is done by proceeding from the, from the leaves to the root. But then I need also to assign virtual activation times, and this is done the other way, from the root to the leaves. So that once I assign to each task an activation time and a deadline, then I can forget about the precedence constraints. This is quite interesting, because this is a way of transforming an application with precedence constraints into another one without precedence constraints, but with activation times and deadlines. And the advantage of this representation is that I can use a classical scheduling algorithm like rate monotonic, EDF. Well, in this case, I need to use EDF because I specify deadlines. But I can forget about precedence constraints, which is, they usually create a lot of problems. So the idea is to derive the step function I mentioned before, the demand bound function, for each flow I decide to allocate. And then guarantee the entire flow depending on the fraction I use. Clearly, in order to derive which is the best parameter, alpha and delta, the minimum I need, I have several possibilities, right? Because this clearly is feasible, because the step function is below the service function. But also this is feasible, right? But this is characterized by longer delay. But then there are other possible feasible solutions. For example, this one is characterized by much less bandwidth, because the slope is proportional to the bandwidth. So clearly, between this, among all these possible solutions, the one who consumes less bandwidth is the one with the least slope. Okay? So, however, the least slope is characterized by zero delay. This means an infinitely small period. So I would like to, in order to achieve this service, I need to implement a reservation with infinitely small period, which is basically impossible, right? Or it requires too high overhead to switch between. So this ideally is the best one, but is the most expensive one in terms of overhead. So if I want to make a realistic minimization, I need to take overhead into account. So maybe considering overhead into account, the best solution maybe is this one. So you see that the problem is not easy, but can be solved. And in fact, this can be, is the bandwidth that can be considered by taking the overhead, this is the context switch overhead, into account if you want to consume a bandwidth alpha with the service delay delta. So you can solve this problem. And so given two different applications characterized by demand bound functions, you can really compute the least bandwidth for each one, considering overhead into account. And then, of course, you can, once you compute this, you know the total bandwidth consumed by your system. Just you sum the two bandwidths together. So this is a way to distinguish two different partitioning of the same graph. So by comparing the total bandwidth required by each one. So clearly, you have to do the computation for each possible partitioning. So you can understand the problem is very complex, and to find the exact solution, the best solution, let's say the optimal solution, this is not polynomial time. This is exponential time, because you need to develop, to explore the entire tree for all possible partitioning, and for each you need to compute the total bandwidth consumed. Of course, you can cut some branches by using some bounds, but still the worst case complexity is quite high. So basically, the problem becomes intractable for n larger than 20 tasks. So you may develop heuristics, of course, and by using heuristics, you can treat, of course, hundreds of tasks. We developed, in particular, a partitioning tool, which, given a graph, you can apply both heuristic search or full search, depending on the number of nodes, in order to find the best partitioning, which consumes the least bandwidth. And the tool basically allows you to specify your application graph. For now, you have to specify the graph manually with the help of some compiler guy the graph could be automatically derived from the source code by using the parallel language. And then the tool provides the bandband functions, and they automatically compute the best possible bandwidth parameter, reservation parameters, alpha, delta, considering the overhead into account. And then the optimization method provides the best possible solution. In this case, the colors represent a flow allocated into a virtual, in the same virtual platform. So here we have two different flows. You can build, several applications with complex precedence constraints. They are handled with the method I just explained you, and you can see the best allocation. Now, I would like to conclude just to pointing out about possible open problem that still remain to be solved. So the first one is the communication delays. This is not trivial at all, because when you allocate a task into a core, into different cores, you have extra communication delays to exchange data. And this was not taken into account in the approach I presented. So this complicates the problem very much. Another problem is shared resources. Different applications, although they are developed independently, they may use the same resources. Like in the cell phone, resources are basically common to all the applications. The screen, the video codec, the keyboards, memory, processor. So there are shared resources you need to, and shared resources usually break the isolation. And then a third problem is adaptivity. You may need to change, depending on the dynamic allocation, you may need to change. So for accounting for communication delays, one method that you could use is to change the computation of the virtual activation time and the virtual deadline by considering also the communication delay. Suppose that this flow is allocated to a core and this flow is allocated to another core. Then, although here you can neglect the communication delay when you pass data, here you cannot. So what you can do is to consider this delay into the computation of the virtual deadline, and so on. But the problem is that delta depends on the allocation, and the allocation depends on the final results, on the optimization you want to achieve. So there is a circular dependency here. It's not easy to solve. The problem of resource is that suppose that two tasks, this task executing a reservation wants to use a shared resource, so must use a semaphore to maintain data consistency. But suppose that the budget allocated to the reservation finishes. So basically this task cannot complete its critical section, has to wait for the budget recharge. Then in this case, if there is another task in another server, in another reservation, that wants to use the same resource, it cannot run because the resource is locked. And this delay is longer than usual because he has to wait also for the replenishment time, which is an extra delay. So there are several approaches to solve this problem. One is to allow the budget to overrun, but this breaks the reservation, so this is not safe because basically you are using extra bandwidth than you are allowed. Or there are other approaches to wait to perform a budget check before entering the critical section. So if you don't have enough budget, then you wait for the next period. But then you see you introduce a longer delay for, and this is an approach considered by a group from Halmstad University. And another approach tries to perform a budget check, but tries to advance as much as possible the next replenishment in order to reduce as much as possible the waiting time. So I mean, there are several approaches, but this problem needs to be taken into account because in reality, different applications use the same resources. And the last problem is to do with very dynamic applications. In most of the cases, especially multimedia applications, they have very variable loads. So if you monitor the execution time of an MPEG player, for example, on any decoder or encoder, you see a lot of variations in the decoding time. So this is not easy. So to allocate a fixed amount of resource. In some case, you may have, you may decide to allocate for the worst case. Then I allocate, the highest possible fraction to guarantee the highest peak in my application. But of course, this is safe, but not efficient. If I have not many resources, this is not efficient. Oh, I could decide to, I don't care about if I have an overload, I don't have enough resources, I allocate less than this application requires. This is of course efficient, but is not safe, right? For critical application may not be safe. So a better approach could be to adapt. So you start with a sufficient level, but whenever you see that the application is requiring more, you may change the level. Of course, whenever you change the level, you need to verify that the other reservation do not suffer. You need to have enough bandwidth to perform an increase here. Or you could even decrease the demand of your application by kind of feedback. So here there are also a lot of degrees of freedom you can use. For example, you may think of different modes each application may run. So in the highest quality mode, you have the best performance, but if you don't have enough resources, you may allow different modes with consumes less bandwidth. And since we have some parameters to tune, like the alpha, the bandwidth we allocate, and the delay, we can think of having a reservation manager at a high level which monitor the entire system and decide to change this parameter in order to maximize the overall quality of service that we have in our system. So I guess I finished here, and if there are any questions, I'll be happy to answer. Thank you.
Thank you, Giorgio. So please ask questions. Yes?
I think in one of your slides you mentioned this utility ratio, which is between U and 2 times U. U is the bandwidth, something like that?
Yes. So the question is, what's the meaning of U in one of the slides I show? Yes, use the bandwidth consumed by the application computed based on the sequential computation time.
And why is the required number of courses between U and 2 times U?
Yes, you have to compute the ceiling. This is a very simple bound. You may find better bounds, but in the example I show you in the slides, there was an example in which you have utilization equal to 1.9, but you need 3 processors, right?
Yeah.
So in the worst case, I can build an example where you need 4 processors. So depending on the numbers you can put on each task, but you can solve always the problem with 5 processors with the example I provided. So, well, it's not easy to, unfortunately, it's not easy to answer in few minutes. You need some computation to provide these bounds, but these are easy bounds that you can immediately derive from looking at the application constraints.
Any more questions?
Yes.
So I was thinking, you present this as an operating system approach.
Yes.
So what comes to you are the tasks.
Right.
Now, for a given application, what tasks you have? You talked about the task graph as the best possible parallelization of the problem. But for a given application, there are many ways of parallelizing it. It depends in what way you program it,
right.
What kind of language. So you could think also of starting with of trying to see this as support for a programming part of the compiler of a programming language, like a kind of runtime system. And then you should generate, as you said, the graph, the task graph automatically. What information would you need to have in the programming language to allow the compiler to generate a task graph?
Okay.
It's not only what parts could
yes.
be done in parallel.
Okay, so the question is, to summarize in a few words, is what type of information is needed from the compiler point of view in order to build the task graph I show you that then is used to verify the timing constraints. Okay, one of course is the information about parallelism, and this can be done by the language or by the annotation. But the key point is that the worst case computation times, and another information that would be useful is that dependencies between portion of codes. So dependencies are also important because they, when a data is passed from one portion of code to another portion of code, it creates data dependency that I need to also take into account in my graph. But the worst case computation times are for sure essential to perform the analysis. And in the graph I've showed, when I said that the best possible parallelization, that it doesn't mean that it's the best possible graph. I meant is the largest possible graph that I can derive. So if I'm able to parallelize as much as possible, then each task cannot be parallelized anymore. So I try to reach the largest possible graph in order to perform. I can do some merging, of course, but and then I would be able. The compiler should provide the execution time for each node.
But the deadline and the activation point you wouldn't need.
Okay, the deadlines and periods, the timing parameters are typically provided by the application designer, depending on the performance requirement that comes from typical control applications. They are required to run with specific periods, and the deadline typically is related to the maximum delay that can be tolerated by the application. So it's really application dependent, and this is not typically provided by the compiler, but is provided by a higher level by the designer of an application by considering the interaction with the environment, which affects the control performance typically.
Do you imagine programming in a language where you can express parallelism? Because the one that provides the information to the compiler is the program that you write in the programming language. But that the information that you get, that the programmer is not concerned with deadlines when he writes the program, but that they come separate.
Exactly.
Okay.
Well, although the programming language could be also, you could think of a programming language that requires the programmer to specify periods and deadlines. But currently, the typical languages used to program application, they don't. So this information is provided separately by the designer.
There's one more question there.
Yes?
Yeah. You said you gain or simplify by replacing the dependency information by activation points or activation time points. But you also lose information that might allow you to change the graph, for example.
Okay.
change the schedule, I guess.
Okay.
Do you see any?
The question is whether...
It was mainly benefits, but I can imagine there are drawbacks. What drawbacks do you see?
Right. The question is whether by converting the precedence graph into activation times and deadlines creates some problem, and let's say I lose some possibility once I do this transformation. Well, the transformation is done to preserve the dependency. So of course, if I change, I mean, if there is some change in dependency, of course I need to recompute all that. But typically dependencies are fixed. I mean, it depends on the code. So if the compiler or whatever provides me the application graph, typically the graph is fixed. I mean, dependencies are not typically dynamic, but in the case of dynamic dependencies, then this approach requires a computation. Yeah. Information that you no longer need, so to say. Yeah, for this type of approach for transforming precedence into timing constraints is good for static graphs. If you have dynamic graphs, then either you perform online, which is a little bit more expensive, but still polynomial time to compute is easy to transform dependency into timing constraints. It's not very complex. So you could theoretically perform online. But if you have a dynamic graph, then maybe some more dynamic approach is needed. But unfortunately, you cannot provide any guarantee in that case. So it becomes a best effort approach.
I think there was one more from Veronica. Okay.
It's the last question.
Okay, we can have two, please.
So in a given architecture, you would normally have features such as instruction level parallelism, pipelines, and caches, things that are supposed to be transparent to the programmer.
Right.
But that could affect the runtime.
Yes.
So are those taken into account?
Okay, that's a very good question. Yes, the question is that there are many levels of parallelism. Some of them are transparent to the programmer, like cache, pipelining, or parallelism that are transparent because they are taken care by the compiler, by the architecture, and there are some more explicit. Well, in this approach I discussed, you can take both into account, but at different levels. So the implicit one, they are taken into account into the worst case computation time. So the compiler, taking into account cache, pipelining, then provides a computation time which takes into account this type of mechanisms. But while the graph, as I showed, then it takes into account the more explicit parallelism from the programming language.
Yeah.
So it's from one of the first slides when you introduced these reservation servers. I think you introduced them in the context of just one processor.
Right.
But you mentioned scheduling the reservation servers.
Yes.
And you listed priority-based schedulers. I would have imagined that it was time slicing. If one, say, 50% of the time, one of them, 1/4 of the time to the other one, and 1/4 to the other one.
Okay, let me go back to the slides.
So what would the priority relate to?
Yes. Okay, the question is, when we implement reservations, should we use a slot-based approach, or also can priority-based approach works? Well, you can use both, because slot-based approach is for sure one approach you can use to partition the processor into different reservations. In this case, these slots are fixed, are the same in each period. Typically, you say, for example, these 2 units are allocated to application 1, and then these 2 units to application 2, and this repeats the same. But in this case, you can also use a more dynamic approach, like a priority-based approach. You just reserve, in this case, 4 units every 10, and then you don't care whether these 4 units are executed at the beginning or at the end. They can be executed anywhere depending on how you schedule the reservations. So if you use a priority-based approach, the highest priority reservation we always run at the beginning. Then the second one we run at, so it's more dynamic approach.
Okay, there's one more question.
Okay.
You mentioned that the compiler needs to take the worst case execution time into account. But if I think of caches especially, then there might be orders of magnitude between the execution time of a single static fragment of code depending on what the cache state is, so that the the worst case execution time basically depends on the mapping and on the migration of tasks across cores or across processors.
Okay. The question is how to take cache effects into account when you derive the worst case computation time, and whether the worst case computation time depends on the allocation. Is that correct? Okay. Well, this is a very complex issue, and then if you want to derive exact bounds, this is not easy. So you have to do some compromise. Well, measurements shows that the cache delay, the cache-related delay affects the computation time for about 40% increase. So it's not an order of magnitude, it's just 40% increase in the really worst case scenario, if you replace the entire cache. So there are mechanisms that reduce these effects. For example, the effect of cache is enhanced by preemptions, because preemption destroyed the cache contents. So I mentioned before a limited preemption approach. So by limiting preemptions as much as possible, but still preserving the guarantee, you can limit this effect very much. Another way is to use cache replacement policies or partitioning. You can also reserve amount of cache locations dedicated to specific applications. Then if you use this approach, you limit the cache effects very much. And then, however, the compiler, the worst case execution time is the output of the compiler, not the input. So the compiler, by analyzing the code and taking this effect into account, should derive the worst case computation time. Then the allocation has also some effect, but you can, if you use these techniques of partitioning cache lines, then you can reduce. Of course, you have to deal with some variations. That is something that you have to deal with.
Okay, I think we finished there. So thank you very much, Giorgio. And as a tradition, you will get a small gift. It's in a new bag that is specifically designed for those who take the Vespa to the work. I guess you are among them. So please enjoy it.
Thank you very much.
And thank you very much. Thank you.
Thank you.
And now there is coffee outside, so we can continue discussion afterwards.
Okay.